Welcome to this presentation in the frame of the Things Conference to empower IoT connectivity. This is precisely the topic of this talk today about expanding the connectivity with a LoRa Generic Node sensor embedding the virtual antenna. My name is Jaume Anguera. I am the CTO and founder at Ignition. First of all, we are going to understand why virtual antenna changed the deal. Then we will show the virtual antenna products and the architecture of a virtual antenna system. Then we will see how easy it is to embed virtual antenna with simple steps. And we will present some electronic design automation tools that can help to accelerate your time to market. Then we will focus on the generic node sensor, and we will compare virtual antenna with other antenna technologies. And last, we are going to give some takeaway. Virtual antenna represents a big breakthrough in antenna miniaturization. As you can see in this plot, we have the first external single band monopole antennas, very big in volume. Back in 1999, 1996, the first internal antennas appeared with still high volume. Then the antennas became more complex, including these complex geometries, and the volume was reduced, still being about 1,000 of millimeter cube. And the big inflection point is with the apparition of antenna boosters, these components of the virtual antenna technology, where the volume is about 10 times smaller than any other antenna product available in the market. So besides being small, they can also be multiband and multiradio. Also, these components are off the shelf, so you don't need to wait to create a new product. So from day zero, you have the component ready to use in your IoT platform. And finally, these components are compatible with a pick and place assembly process. So this means that it reduces the risks when building thousands of thousands, hundreds of thousands of components into your PCB. Virtual antenna products can operate for any frequency band, any wireless protocol, and for any PCB. For example, in this picture on the left, we have three representative devices, from a big one to a small one, such as a smartwatch. And no matter the form factor, we can always rely on the same antenna booster, this component in red. And the only thing we need to change from one device to another device is the design of a matching network, which is faster and easier than designing an antenna from scratch. Also, antenna booster can operate for any frequency band. This means that for one particular device, we seek operation at LoRa, for example, LoRa 900, so we can use the same antenna booster that the one that you can use in a multi-band device, for example, one that needs to operate at narrowband IoT, LTE-M, so at several frequencies. You don't need to change the antenna design. You can use the same antenna booster, and from one device operating at LoRa and to the other device operating at the several frequency bands of narrowband IoT, you only need to change the matching network. So as you can see, designing wireless devices, IoT devices, embedding virtual antenna is a totally different approach. It's not the antenna that determines the frequency bands of operation, but the designer who freely chooses the frequency to operate at thanks to the design of a matching network. Virtual antenna products are already adopted in many IoT devices. In here we have some of the flagship devices for IoT from Nordic Semiconductor, Sequans, Sierra Wireless, and Capri Wireless. These are examples for the cellular IoT space. The red component is a virtual antenna product. And in here we have one for LoRa 900, which uses this tiny antenna booster that we are going to talk about, which is the generic node developed and designed by the Think Industries. Here we have the family of the virtual antenna products. In fact, with one product, we can operate at any frequency from, say, 600 megas up to 10.6 giga. So everything for narrowband IoT, 4G, 5G, GPS, Wi-Fi, ultra-wideband, and so on. But there are some antenna boosters that are unique for a particular application. For example, in this case, we have the Duo MX10, it's only 7 mm in length, that is very suitable for those applications, including GPS and Bluetooth simultaneously in the same antenna piece. Also, we have the Trio MX10 that can use not only 2 radios, but 3 radios within the same antenna chip. And the 1MX10 is the component that has been used in the generic node. The virtual antenna architecture is very simple. We have 3 parts. 1 is the antenna booster, 2 is the matching network, and 3 is the ground plane. The antenna booster is usually located on the corner of the ground plane. The ground plane, at least you have 2 ground planes, 2 layers of ground plane in the multi-layer PCB, one on top and the other on the bottom. Then we have the matching network to allocate the matching network comprising lamp components, capacitors, and inductors. And then we have the transceiver, the RF module, in charge of transmitting and receiving the information. Then the matching network, what it does is to maximize the power emitted by the transceiver so it reaches the antenna booster and it radiates into space. Thanks to this architecture, virtual antenna products can be 10 times smaller than any other product in the market. Let's see how a matching network can shape the frequency response of your device. Imagine we have a device with an antenna booster. By designing a simple matching network, we can have operation at a single band. In this case, it illustrates a frequency and the S11, so this will be an example for LoRa 900. If we now need to operate at several frequency bands, such as 800, 900, plus 1800, 1900, and so on, we can now design a different matching network, in this case with more components, to achieve this multi-band response. And in case we want to expand the frequency bandwidth up to 10.7 gigas to include more frequency bands of the narrowband IoT LTM, then we can design a new matching network. As a result, you see that we can obtain this multi-band matching network. So as a result, designing wireless systems embedding virtual antenna relies not on shaping a new geometry on the antenna, but by just modifying a matching network. Besides being fast and simply, all these matching networks can be designed by software in automatic fashion. So most of the microwave simulators available in the market can do these matching networks, not only the topology, but as well as the value of each capacitor and inductor. For example, we have Opteni Lab from Opteni, the Microwave Office from Cadence, and ADS from Keysight. All these softwares are available of doing a matching network synthesis. What is the role of the ground plane? Well, here we illustrate a small ground plane, a PCB area, including a ground plane, 10 centimeters squared, to a medium and to a large PCB. And on the vertical axis, we have the efficiency being the best efficiency, the 100%. As you can see in blue color, there is a strong dependency on the efficiency depending on the PCB size. So as you increase the PCB size at around 900 megas, you can get more efficiency. But in the high frequency region, it means for frequencies larger than 1.7 giga, the dependency is not as critical, it's more or less quite flat. So the challenge here is to design wireless devices having operation in the lowest frequency region. So everything below 900 megas more or less. So besides having marketing needs in determining the size of the PCB, we should also put into the equation the PCB size in order to get the best performance out of our IoT device. Here we have some examples on how a matching network can shape the frequency response of your device. In here we illustrate a ground plane of 131 millimeter with an antenna booster. In this case, it's a very small antenna booster, 12 millimeter, which represents only lambda over 30 and 900 megas. By simply designing a matching network that should be on this area, in this case it's a combination of two components, two inductors, we can have a good measured SWR and a good total efficiency measuring an anechoic chamber. You can see that the total efficiency is more or less 90%, in spite of using a very small antenna booster. Now, if we have another device that we need to change the performance from single band to multiband, the only thing we need to change is the matching network. As you can see in this example, everything remains the same as the previous device, and the only thing that changes is now the matching network, that instead of being two components, now we have 5 components. As a result, we have in blue the total efficiency that has over 70 and 80% in a first frequency region and in a second frequency region. And even more challenge. Imagine we want to expand the performance in this high frequency region up to 2.7 giga. What we can do is, again, is to design a new matching network. In this case, we have 7 LAMP components, where we can expand the bandwidth, reaching efficiencies of 70% beyond in this frequency region of 1.7 up to 2.7. So again, the matching network plays a very essential role in shaping the frequency response on your device. Yet another example, in this case we have the one MX10 as the one used in generic node, and with a small clearance area, everything is the ground plane, and in this case we don't have any conducting layer nor any trace, free of any metallic component at any layer of the device. And again, with a matching network, we can shape the response to have a first frequency region and a second frequency region. Let's see another interesting feature about virtual antenna. So besides being small and multiband, virtual antenna products can be multiradio. This is the example of the Trio MX10. So imagine that we need to operate at 3 radios at the same time, one for LoRa 900, another for GPS, and another for Wi-Fi. The common sense approach will be to use 3 different antenna boosters for each radio. Each antenna booster will be connected to a different transceiver. This occupies space on the device, and this is not an optimum solution. However, thanks to this flexibility in virtual antenna, we can have 3 ports on the same antenna chip. So one port will be for LoRa, another port will be for GPS, and another port will be for Wi-Fi. So in this is more cost effective, we occupy less space, and we allow more space to integrate other electronics, batteries, sensors, and other kind of components that we need in our device. In here we illustrate how we can engage a triple radio component, the Trio MX10, with an existing transceiver having 3 radios. In this case, it's a Centec transceiver, the LR1110, that allows 3 radios, so it's very convenient to connect the Trio MX10 to the Centec chip. In this application node, we show how these 3 radios behave as a function of different ground plane sizes and also versus different environments for wood, concrete, metal, and so on. So please have a look at our application node where you will have plenty of tips and you will get the performance that you can get based on the ground plane size. Embedding virtual antenna in a wireless device is very simple. The first step is to select the antenna booster and place close to the corner of the ground plane. Usually we should have a clearance area free of any metallic component. Second step is to design the matching network. As we saw, the matching network is between the antenna booster and the transceiver, and it has the mission to maximize the power from the transceiver that goes into space, and also to maximize the incoming power from space to be transmitted into the receiver. And last is to ensure that everything works properly, is to test the response in terms of S11 with a vector network analyzer and also the efficiency with an echoic chamber. Please have a look at these videos where you can get more information about this process. So placing the antenna booster at the corner of the ground plane is the best in order to obtain the better bandwidth and efficiency. Here you have some examples. In here we have an antenna booster with a feeding line that reaches a matching network, and then we have a 50 ohm transmission line that reaches the transceiver. Here we have another example with the Trio MX10 with a feeding line, again close to the corner of the ground plane, and then the matching network that reaches the transceiver. How we can change the input impedance thanks to a matching network? Well, it's very simple. In here what we have, it's an antenna booster, it's very small, λ/30, on a ground plane in yellow color. Without any matching network, the input impedance is reactive and it is very far away from the center of the Smith chart. So it is very poor match. In terms of S11, it's about -1 dB. This means that most of the power that the transceiver will inject into the matching network will be reflected back and the efficiency will be very poor. But thanks to a matching network, we can move these markers 1 and 2, representing LoRa frequencies, to be very close to the center of the Smith chart. And as a result, these points 3 and 4, now they have a very good S11, a very good matching, thanks to the addition of a very simple matching network. So as you can see, by including this network, we can not only match at LoRa 900, but at any other frequency. And not only for single band, but as we saw in the previous examples, we can sophisticate the matching network to include several frequency regions. Now let's deep dive into this smart generic node sensor platform developed by the Think Industries with technology of ST as microchip and as well as virtual antenna, as you can see in this one MX10 antenna booster. It has plenty of sensors, as you can see in this table. First, we have the antenna booster. It's very small. It's only 7 by 3 by 1 millimeter. The location of the antenna booster usually should be at the top edge and close to the corner of the ground plane with a clearance area, you can see in this blue area, free of any metallic component, not only on top, but at any layer of the PCB. Then you have to include a feeding line that goes to the ground plane where you have the matching network components and a 50 ohm transmission line that reaches the front end module part. Again, if you need some help while you are designing your IoT device based on the generic node, you can always use the fast track to assist you. Some other details about the matching network. As you can see here, these components, these are LAMP SMD components, typically 0402 in size. In some other cases, you can use smaller ones, 0201, and also bigger ones, 0603, in case we need to obtain a high Q. What is important is typically 0402 works well, and they should be high Q and with tight tolerance, which are available by any vendor. Then, after the matching network, before reaching the front-end module part, usually you will have a transmission line. The shorter the transmission line, the better. And in this case, this is a 50 ohm transmission line. It's a coplanar waveguide, and you should have bias on each side along the transmission line. In this case, the output power is for 14 dBm and 22 dBm, and all schematics are open. You can consult, you can go to the Think Industry webpage with the generic node, and you can adapt your schematic to your own needs. As we illustrated before, in one of our services, we can take into account your device, fully populated, including the batteries, several PCBs, and determine if we need more clearance, which is the best antenna location. And in return, besides S11 and efficiency, you get the matching network and also the radiation pattern, so you can have a look where this device is going to radiate or is going to receive the information. Also, if this device is going to be in a very complex environment, on top of a container or in another sophisticated scenario, we can also take that in consideration in the simulation phase. Now let's see basic electronic design automation tools that can help you in designing your wireless device so you can accelerate your time to market. First of all, what we have is a very useful tool. It's called libraries. For the first time ever, in the Microwave Office Circuit Simulator by Cadence AWR, we have these libraries that it's a set of files containing S-parameter data representing several PCBs with several antenna boosters. So as you know, in a microwave simulator, you have libraries for diodes, transistors, capacitors, inductors, amplifiers, and filters, but not for antenna. Now in this case, you can get the S-parameter for a device with a particular dimension and with a particular antenna booster. So if you want to know if the performance of your IoT device is going to meet a particular bandwidth, you can use this library by taking a device, a library that has a similar size that your target device, and do the matching network analysis to see if you can get enough bandwidth or not. And if not, you can always try another PCB with a different size till you get enough performance. Let's see how it works. There are a set of more than 40 different ground plane sizes, and imagine that we want to analyze if our generic node has enough bandwidth for LoRa 900. So we go to our library files and look for the closest ground plane size to our device. So once we have the ground plane, we have that file, and The second step is to select the antenna booster. In this case, we want to have a very compact size, so we choose the 1MX10 antenna booster. So this antenna booster with this ground plane looks very same to this device you have in mind at the very beginning of your project. So this library contains the S parameter for this scenario without any matching network. Now it's up to you to test in a very simple way if you can get enough bandwidth for your application. So the file at the end looks like a very simple raw data. What you have is a file that contains for this ground plane and this antenna booster frequencies and the S11 in real part and imaginary part. Please have a look at our user manual that you will see step by step how to easily use this library. Let's see an example. Let's imagine that we are at the very beginning of our project, of our generic node. So we select our PCB size in this library. Also, we select which is the best antenna booster. We define the frequency bands of operation and a target, maybe a target of S11 or maybe a target of efficiency. And that's all. This is the enough input data that the software needs to start analyzing millions and millions of matching networks to get the best matching network, the best topology, and the values to satisfy the target specs. If there is a solution, this smart matching network synthesis tool will find the matching network. If not, it will give us in return the closest matching network to attain the best response. And if it happens that if that response is not good enough, then we can always go to the very first step, choose another ground plane bigger, because as we know, the bigger the ground plane, the more bandwidth we can get, and repeat the analysis till we get a satisfactory response. Let's see this example. We choose the PCB, the ground plane, well, in this case, the PCB is 60 by 30 with a ground plane. We select the antenna booster. This is the one, 7 by 3 by 1 millimeter high. We are going to select this frequency region of LoRa for Europe. And we specify a target of S11 less than -7 dB. With this input data, now we go to the microwave AWR software, and let's see how fast and easy it is to do the design. This represents the input impedance of this PCB 60 by 30, including the 1MX10, and this is this library is included in the software. You can see the response in terms of S11 versus frequency. It's a very poor response. So now what we are going to do is we are going to design a matching network. So we go to a network synthesis tool. We define the frequency region of operation. We select the components, inductor and capacitor, and the maximum number of sections. In this case, since this is going to be a single band operation, with 4 components, we have more than enough. We can also adjust the minimum and maximum value of this inductor and capacitor, and other features that you can have a look in our user manual. And this is ready to set the target. Now we set the target of having an S11 below -7 dB in the LoRa Europe frequency region. So we set the minimum and maximum frequency, and the goal of S11 should be -7 dB. And that's all. Now it's ready for the synthesis tool to do the magic, and as a result obtaining the matching network. Now we have 2 matching networks, so you can always test both matching networks. Both satisfy the target of S11 below -7 dB, As you can see, cost 0 means that both achieve the target. And this is one of the matching networks. It's a series component plus a shunt component. In this case, we are using ideal components, but also the software can select commercial components. Let's see what is the response in terms of S11 in blue without matching network and in pink with the matching network. You can see we have a very good S11 within the LoRa Europe frequency regions. Now, if we need to tune to another frequency, we can repeat the experiment, or perhaps a very simple way is just to tune one of these components. So let's illustrate what happens if we tune the first component, which is the serial inductor, and as a result, now we see that by changing increasing this value, we can operate at LoRa about 780, and if we decrease this value, we can now match to LoRa around 928 megahertz. So it's very simple and it's very automatic. Also, another tool that you can use for those having the CST Studio Suite, now you have all our virtual antenna products available through the Encrypt models. This means that you can get the model into your CST and do your own stuff. Here you have an illustration. This is the real Trio component, and this is the Encrypt model. So it has everything is the same, the look and feel, the materials inside, everything. So it's ready to use. So there are plenty of data of user manuals on how you can import these Encrypt models into your CST models. In this example, we illustrate how we can import an Encrypt model, which is the Trio, into a real IoT platform, including many components. You see in yellow the ground plane, the battery, and in green we have the substrate, the clearance area free of any metallic component. So now with this you can simulate your S11, you can design your matching network, including also the casing, and this is an example from the Thingy 91 from Nordic Semiconductor. As far as matching network synthesis is concerned, you have some available tools such as Opteni Lab from Opteni, Microwave Office from Cadence AWR, where you can easily obtain the matching network considering real components. In a bid to further see the advantage of the automatic design process, in here we illustrate the total efficiency obtained by a matching network designed by human force and the matching network in blue obtained by this automatic process based on matching network synthesis. As you can see, the results are even better for the blue case, which is the software base, and especially in the high frequency region. So not only the results in this case are better, but one component less is used in the matching network, and the most important, the time to design the matching network and to build into a real PCB, it took less than a couple of hours. Whereas in the human force, it took several days to find the best matching network after a trial and error process. So as you can see, this automatic process, it's fast, it's easy, and it's very reliable. At Ignion, we have several services that can assist you in accelerating your time to market. The first one is in the conception phase, which is the fast track service. Based on a scheme of your PCB and the frequency bands of operation, in return, we provide which is the best antenna location and which is the best antenna booster, some basic recommendations, the results in terms of the efficiency, and which is the bill of materials of your matching network. In case those results are acceptable, then you go to the next step, and if not, you can take action and test another ground plane in order to get better performance. A second service, in case you have the mock-up with the components, the batteries, and the casing, and you need to test what the performance will be, we can take those components into consideration and again simulate and provide the best matching network, the best antenna booster, and the results you are going to obtain in terms of S11 and efficiency. Once you have the real PCB, the real device, we can also assist you in designing and implementing the matching network into your real physical device, considering not only the PCB, but the PCB fully populated with the battery and also including the casing. So with that, you get the matching network that best operates into your device. So as a result, you also obtain the S11 and the efficiency measured in the anechoic chamber. And last but not least, we can also assist you in the certification, in measuring the TRP, and also providing the new matching network in case you need to tune to fulfill a particular channel. We invite you to test our fast track service. Here you have the QR code, and this is a very fast service, usually less than 24 hours, based on your input data, which is very simple, the PCB size and the frequency bands of operation. You will get which is the best antenna booster, the location of the antenna booster, some basic recommendations such as the clearance area, and an estimation of the performance in terms of S11, impedance, and efficiency. Now let's move to the end of this presentation. Now let's compare virtual antenna with other solutions, in this case flexible printed circuit antennas. In this case, what we illustrate is a comparison for frequencies in the 700, 960 plus 1.7 up to 2.69 giga. You can see an antenna booster, it's pretty small, it's only 12 mm by 3 mm by 2.4 mm high, in the same PCB as in this FPC antenna. The FPC antenna has been placed at several heights, the same height as the antenna booster, which is 2.4, then increasing to 5, 10, 15, and up to 20. And as you can see in the results, in red we have the total efficiency measured in the anechoic chamber, always is much better than the FPC antenna. For example, in the FPC antenna, in particular in the low frequency region, when the high is the same high as the virtual antenna, the performance is 50 times less in efficiency of the efficiency you get with virtual antenna. Even with the high of 20 millimeter, which is a very thick device, the efficiency is pretty below the virtual antenna. In the high frequency region, this is not as critical, but always the antenna booster performs much better while keeping a very compact antenna volume. And not only that, there is another concern, another issue, another drawback with this technology is that depending on the position of the FPC on the PCB is going to change the performance. So this is not predictable once you need to build hundreds of thousands of these devices. Whereas virtual antenna, once the position is fixed, you will get always the same performance. And last, now here we compare virtual antenna with self-resonant antennas, and you can see the typical volume of these self-resonant customized antennas. It's about 100 millimeter cube, whereas it's less than 100 millimeter cube with virtual antenna. In terms of adjusting the performance in a real device, either in simulation or in the lab, it takes time because you need to tune the antenna by shaping the geometry. Whereas with the virtual antenna, we only need to change the matching network, which is very fast and very simple. In this case, you have to be an expert to design the antenna. However, with virtual antenna, any RF, microwave, or wireless engineer dealing with components and matching network for filters and amplifiers can easily tune the response of the virtual antenna. About the reuse of these self-resonant antennas for other platforms on other frequencies, well, it's difficult because once the antenna is resonating at some particular frequency, it's difficult to have performance at other frequencies. However, with virtual antenna, since this is a non-resonant element, you can add a matching network to tune the frequency response wherever you want. In terms of integration, well, these antennas are small, but maybe not small if the device is very, very slim or very, very narrow. Imagine you have a device that it's only 20 millimeter width. This antenna simply does not fit in. However, a virtual antenna, in this case, is 12 millimeter, so your device can be very narrow. And for those applications where you need MIMO, well, with these solutions, perhaps you are limited to MIMO 2x2, but with virtual antenna, you can have 4x4 in case you use the 4 corners, and even you can go beyond. So to sum up, when designing your IoT device, you should think on the antenna first in order to get the best range, the best efficiency, and the best battery life for your device. Virtual antenna products, as we saw, they can operate for any frequency band, any protocol, for any form factor, thanks to a proper design of a matching network. Virtual antenna products are 10 times smaller, which is very suitable for embedding those components in a very small PCB size. They are off the shelf and pick and place. So this ensures and minimizes the risk and ensures a good quality when assembling many hundreds of thousands of components in the mass production. You can easily embed virtual antenna thanks to the electronic design automation tools, as well as using our supporting services. And last, we saw that this smart generic node sensor, it has the virtual antenna on it. It's a very small component, and as well as the generic node itself, it's very small in size, very suitable for any kind of IoT application, and you can easily adapt your hardware and software to your needs, thanks to this open concept of the generic node developed by the Things industries. So with this, we hope you like the presentation. We hope you find it interesting, and keep in touch and stay tuned. Thank you.